Hello, my name's Steve Young. I work for Deepwater Corrosion Services. Deepwater is the originator and manufacturer of a product called IROD brand anti-corrosion pipe supports. Today we're going to talk about causes and preventions of corrosion at the pipe support. This is a really common failure point, and it is the leading cause of external corrosion failures for above-ground piping systems. On this slide, in these images, you can see on the left, there's corrosion happening where the pipe is sitting directly on the support. Same thing on the right. You can see there's no damage to the coating that's not in contact with the support, but where the pipe is in contact with the support, you can see the coating is damaged and you start to see some corrosion happening. So there's some misconceptions about how this corrosion happens, but right here we're going to talk about how this really happens. The round pipe sitting on a flat support creates a crevice at the bottom of the support. Condensation or rain, water collects on the outside of the pipe, and then gravity pulls that water down to the bottom of the pipe, and the water gets trapped at the crevice. The problem with that is that the coating on the pipe and the coating on the support is an atmospheric coating, which means that it's meant to be out in the atmosphere or dry most of the time. But here at the bottom where this crevice is and where water is trapped, the coating is in contact with water all the time, which is similar to being put in an immersion service. Eventually, the coating begins to soften and separate from the steel, and then you have bare steel in contact with the oxygenated water. Once the coating is separated from the steel, you start to see progressive undercutting of the paint. And then you see localized wall loss, which becomes a real problem. Here's the truth about what happens. The pipe sitting on a flat surface creates a crevice. The crevice traps and holds water. That damages the coating. And then you have the pipe sitting directly on bare steel, which electrically grounds the pipe. And a wide support creates a bigger area of concern or a bigger area of problem. As you can see in this image, a nice wide beam, and the corrosion is happening all along the surface of the pipe that is in contact with the support, but you don't see the same thing where it's not in contact with the support. So like I said, there's some misconceptions about how this happens. The first one is that a lot of people believe that this is a galvanic thing, that the corrosion is happening because there's two dissimilar metals in contact with each other. So they believe that if they stick something in between the pipe and the support, like a piece of rubber, that they'll eliminate the corrosion at the pipe support. So a lot of times they use rubber pads, as I mentioned, but there's a problem with rubber pads. The problem with rubber pads is that they actually trap more water. They become very porous and trap more water. They hold this water against the pipe, and they prevent the evaporation of the water. They also make it really hard or impossible to inspect. Here's some examples of what rubber pads look like after some time in the field. You can see here on the left there's some really thick rubber pads that have been installed underneath the pipe. And you'll notice in the image that there's those dark lines or cracks in the rubber. That happens over time. The rubber becomes more porous and traps and holds a lot of water. And you can see that that whole area that's in contact with the pipe, lots of corrosion's happening. It actually is accelerating the corrosion issue because there's more water in that location than there would be without the rubber. Here on the right image, you can see that it's a thinner rubber, so it doesn't smash quite as much, but it's curved and shaped, and it's acting a little bit more like a funnel. It's actually funneling more water into this crevice and accelerating the problem in the same way that the rubber on the right is. But there's a solution. The solution is IROD, which is a product manufactured by Deepwater. The way that this works is by lifting the pipe up and resting on this half-round surface of the IROD, water can no longer be trapped. It also allows air to circulate and evaporate the water. The raised pipe also makes inspection easier. By inserting the IROD, you do eliminate metal-to-metal contact, which is a secondary benefit, which can accelerate corrosion. IROD's tough thermoplastic material also isolates electrically and thermally, which is good for cathodic protection systems. And the way that this works is, when the pipe is underground, there's a cathodic protection system that is in place to protect the pipe underground. Then the pipe comes up out of the ground and it's resting on top of a pipe support similar to these ones here in the front. When that happens, if the pipe is grounded, with the coating is removed and the bare steel is in contact with the support, and the pipe is grounded to the support, then the cathodic protection system can be drawn to that base of the support, which then causes the cathodic protection system at the end of the system to fail prematurely, which can be very costly. However, if you install IROD and isolate the pipe from the support, you eliminate the possibility of this happening. IROD is an extremely durable thermoplastic material. It's a proprietary hydrophobic material, which means that it sheds water. It doesn't absorb water like the rubber pads we mentioned a moment ago. It has excellent UV stability. It's proven to last 28 years or more in the field, has low creep, which means that it does not smash or change shape when a load is applied. It has a high compressive strength. Our 1-inch I-rod material can support an 8,000-pound point load. The 1.5-inch can support a 10,000-pound point load. There are 3 different material types that we offer. There's the standard white I-rod, there's the I-rod HT or high temperature, which is an amber color, and then the peak, which is a tan color. And the difference between these materials is the temperature range. So the standard white I-rod, we've tested it down to minus 166 F. It has a maximum operating temperature of positive 181 F. If the temperature of the pipe goes higher than that, then we recommend the I-rod HT amber, which goes up to 340 degrees Fahrenheit, or the peak material, which is tan, it goes up to 480 degrees Fahrenheit. There are several ways to install I-rod. The first one is a beam dressing. You can see in this image they were installing galvanized steel beams, and there's multiple pipes on that rack. So in order to select the proper I-rod for this application, you choose the largest pipe or the heaviest weight and select the I-rod that's appropriate for that weight. In this particular case, it was 1.5 inches, and they could have used just one piece of I-rod on this rack. You'll notice that they have 2. The reason that they installed 2 is they were concerned that if they put the I-rod on one side of the beam and all the weight of all the pipes might cause the beam to bend, and then the beam could come in contact with the pipe on the other side. So they installed 2 pieces of I-rod to distribute the load more evenly. And then you'll notice they have drilled holes in the end to bolt down the I-rod. We also offer an I-rod adhesive. I-rod adhesive is an easy way to attach I-rod without drilling holes. We always recommend bolting first. That's the most secure way of attaching the I-rod. However, there are times when bolting is not optimal or not possible, and that's the time when I-rod adhesive can be used. It's a really simple 2-part epoxy. It applies with the gun very simply. Temperature ranges are very similar to the standard white I-rod, minus 166 up to positive 181. But as I mentioned, we always recommend bolting first. Now let's talk about some other ideas that just don't work. These are other pipe support designs that just don't work out in the field. The first bad design is uncoated U-bolts. You'll notice in this image that there's damage to the top of the pipe. This damage was caused by the bolt. I don't know if you've ever held a galvanized bolt in your hand, but it's a really rough surface. There's imperfections and large chunks of metal on the bolt. And when you're tightening down the bolt, that chunk of metal can pierce through the coating and allow moisture to get in under the coating and cause this type of damage that you notice at the top of the pipe. Or if the pipe moves around and the bolt rubs against it, you can have the same damage. As a solution, we offer our bolts with a poly-shrink coating. This is a cross-link polyolefin. It's UV stable. Protects the pipe during installation and then during use. A lot of people believe that the coating is on the bolt to protect the bolt. It's not. It's there to protect the coating on the pipe. We offer 2 different types of shrink. The first one is our standard poly-shrink, which has a maximum operating temperature of 230 degrees Fahrenheit. We also offer a high temperature material, which goes up to 428 degrees Fahrenheit. There are 3 different bolt coatings that we offer. The first one is hot dip galvanized, the second one is 316 stainless steel, and the third one is Cermagard. You're probably all familiar with what hot dip galvanized is, and you may be familiar with 316 stainless steel. May not be familiar with Cermagard. So Cermagard is a ceramic-based coating that was first introduced in the 1960s for the underside of automobiles up in the northern United States. When it snows, they put salt on the road, the snow melts, and then you have melted snow with salt or salt water splashing up on the underside of the automobiles, which makes it very difficult for the maintenance guys to remove the nuts. So DuPont came up with this product called Cermagard for those particular applications where salt water is splashing directly on the underside of the automobiles. We offer this as a coating on our bolts for the same situations where salt water is splashing directly on the bolts. So this would be good for docks or jetties or the legs of offshore platforms. Previously we talked about using I-rod as a beam dressing where the pipes were not secured in place. There are times, however, when the pipe needs to be secured in place and a U-bolt is needed, and for that situation we offer a Nu-bolt. Nu-bolt includes the coated U-bolt with the poly-shrink, as I mentioned earlier, cut and drilled I-rod, and 4 nuts, as shown here in this image. Another bad design that's really harmful to pipes is metal pipe guides. So this is you can see here in this image, this is a C channel, a metal C channel that's been welded vertically. And the idea here is the pipe obviously is moving longitudinally, and they need to have some type of guide that keeps it in place so it doesn't fall off the support, but allows it to move. But you can see everywhere where the pipe is in contact with the beam, the coating has been completely removed, and now you have exposed steel in contact with the atmosphere, which causes corrosion. And these repairs can be very costly. Here's another example of the same idea. Over on the left, there's an angle that's been welded kind of like a pyramid, and on the right, these are angles welded vertically. Same thing is true here. Wherever the pipe is in contact with these metal guides, the coating is completely removed, and you have steel in contact with the atmosphere, which causes corrosion. As a solution for this, we offer non-gripping new bolt. And the difference here, you'll notice on the left, the gripping. So all the nuts, there's 4 nuts that are on the bottom, and those nuts are tightened down, and the U-bolt is clamped down on the pipe, holding it in place. The center image is non-gripping. You'll notice that at the ends, we've machined a flat area. There's a nut sitting on top of that flat area. Then when you loosen the nuts down the threads, it raises the bolt up and creates a little space on the top, which allows for the pipe to expand and contract with thermal change or move a little bit. If the pipe is moving a lot, then we recommend our non-gripping Excel new bolt. Same thing here, we've got a flat machined end with a nut on top. Loosen the nuts down the thread, creates a space on the top. The difference between XL and non-gripping is that there's a little bit wider inside gap on the XL. It's a 1/2 inch wider, which allows for some space all the way around the pipe so the pipe can move freely without being held down in place. It acts more like a guide. This just allows the pipe to move back and forth longitudinally and expand and contract due to thermal change. Another problem, and in my opinion the worst problem for pipe supports, is FRP wear pads. The problem with wear pads is that moisture can get in between the wear pad and the pipe, and when that happens, corrosion is happening and it is hidden. Some major drawbacks to using these FRP pads is that the loose pads allow water to get trapped. The pad makes it impossible to inspect. You can't see the space or inspect that space that's in contact with the wear pad. And the problems don't really appear. You can't see them until that corrosion grows outside of the covered area of the pad. And this failure can be catastrophic. Now, the folks that sell these FRP pads, they'll tell you that moisture can't get in, and these are just glued on the bottom with a little caulking or some sealant around the edge. The problem is that steel and fiberglass have a different coefficient of thermal expansion. So the steel is expanding and contracting from thermal change at one rate, fiberglass at a different rate. Something has to keep up with one moving a lot and the other one moving less. And in the beginning, the adhesive can keep up with that, but eventually it separates and allows a little crevice. You just need a small pinhole for moisture to get in. Moisture gets in, starts to have corrosion happening, and that's what you see here in this image on the right. The pad is completely separated, moisture's gotten in, and there's lots of corrosion happening. This is a cautionary tale of a company who used those fiberglass wear pads. So this is a pipeline operator in the Midwestern United States. They had installed a pipe support similar to the one here on the table in the front on the left, flat piece of metal with 2 new bolts on it to support the pipe. After about 8 years, the person that was managing that pipeline moved up the chain in the company to a different position, and someone else came in and filled in that position to manage this pipeline. For some reason, I don't know exactly why, they decided to remove many, not all, of the flat supports with the 2 bolts and install a curved saddle similar to this one here in the front, as you see in the image, with fiberglass FRP wear pads. So they installed these on several or many or most of the pipe supports, and after 1 year, those fiberglass wear pads separated, moisture got in, they started to see corrosion issues. Cost them approximately $700 per location to repair that. They went to the fiberglass wear pad person and said, "These didn't last very long. You said they would last forever. They've only lasted a year. They've already failed." That person said, "Well, the adhesive that we were using last year wasn't very good. We have a really great adhesive now, and this new adhesive, it's fabulous. It's going to last forever. We'll just install it with the new adhesive, and it'll do like it's supposed to." So they spent approximately $1,000 per location to reinstall new fiberglass wear pads. And you can see here this image, the line that's at the top of the wear pad is the first FRP pad that was removed, the damage from the first one. And this, a year later, is the second one that's shown here, this dark area around the FRP pad. So it only took another year, failed the same as the other one. That's when this operator contacted me and asked me why the pipe supports where I-rod was still installed on the flat, there was no damage. 11 years later, pipe still looks great at those locations. However, where these FRP pads were installed, it's already failed twice in 2 years. So I went and explained to him how moisture gets in. And since then, they've removed all these FRP pads. They no longer allow those FRP pads to be installed. They specify I-rod by Deepwater only. Another bad design is 360 wraps. These are similar to the fiberglass wear pads. It's a fiberglass wrap that's wrapped around the pipe. And the same thing happens here. Thermal expansion is happening. The coefficient of thermal expansion is different between the fiberglass wrap and the steel. So one is expanding a lot, the other not so much. A crevice is formed, water gets in. And that causes corrosion underneath the wrap. This is an unseen corrosion. You can't see it because it's all covered up. And the worst thing is this can be a 360-degree damaged area. You'll notice here on the right there's corrosion pitting and metal wall loss happening almost all the way to the top of the pipe because the fiberglass wear pad has allowed moisture to get in and trap it against the steel pipe. This is the worst case of all of them. This is a Marcus Hook refinery. They had an event back in 2009. The image here on the left you can see as the event is happening, and then on the right is the day after they put the fire out. It's all been cleaned up, but you'll notice millions of dollars of damage. So what caused this? The same thing happened here. They had a curved, this is a metal pad that was installed underneath the steel pipe. They were having some damage from the pipe moving around. They wanted to stop the pipe from rubbing against the support, so they thought if we just put a curved metal pad in between, then the curved pad will take the damage as opposed to the pipe. The problem is moisture got into that curved area and held it against the pipe. You'll notice here on the right, this is an 8-inch high-pressure gas line. It only took a small pinhole leak of that gas, ignition source close by, ignited the gas and blew up their plant. So one of those FRP companies that sells the FRP pads purchased some I-rod from us unknowingly. They were trying to prove that FRP pads were better for wear resistance than I-rod. So purchased a piece, hired a third-party laboratory, had a 2-inch steel pipe that was moving back and forth something like 5,760 times per day. Then they published the evidence from that report, and we saw that online, and we captured it. This was photos from their report, and they said, look, after 7 days of their test, which at that time had 40,320 movements of the pipe against the I-rod. It's already worn through the first layer of a 3-part epoxy coating. Now we took that information and said, most times a pipe's not moving 5,000 times a day, so we assumed sun comes up, pipe warms, it heats and expands a little bit, sun goes down, it cools and contracts. You turn something on, maybe it shifts the pipe a little bit, you turn it off, maybe it shifts. So we assumed 4 movements of the pipe per day. If you assume 4 movements of a pipe per day, it would take 27 years for the pipe to move 40,320 times, or 27 years to wear through the first layer of a 3-part epoxy coating. Following that same logic of 4 movements per day, it would take 58 years to wear through the second layer of the epoxy coating and expose the primer. You'll notice there's very little damage to the I-rod at this point. Following the same logic, it would take 125 years to wear through all 3 layers of the coating and actually expose the steel. Again, very little damage to the I-rod. So, thank you very much to the company who paid for this test for us. We did not know that I-rod was such a great wear-resistant material, but now we do, and we can promote and sell it as a wear-resistant material. Another problem area is clamps, cradles, saddles, pipe shoes. The problem with saddles or clamps or pipe shoes is that same issue. It's a curved area that traps water, holds that moisture against the coating, which then damages the coating, exposes the pipe to oxygenated water or the atmosphere, which causes corrosion to happen, and inspection can be very difficult or impossible. As a solution for this, we create I-rod clips. I-rod clips are made from the same field-proven I-rod material that we use for our flat supports. We just machine out a section so that the I-rod clip can clip onto the clamp or saddle or pipe shoe or pipe hanger. It thermally and electrically isolates the pipe from the support, allows water to evaporate, and makes inspection possible. You can walk up and see the space in between the pipe and the support, and you can tell if there's a problem with the coating and fix it before it becomes a major problem. Here are some images of how I-rod clips are installed. You'll notice on the left this is a pipe hanger, and you've got various pipe clips installed on the pipe hanger. Second one here is a a pipe saddle, you'll notice that there's no eye rod at the very center of the saddle, or 6 o'clock on the pipe. That is because that would create a crevice that could trap water and cause corrosion. So each piece of eye rod clip has a little strip of double-sided tape on the inside. You just remove the paper, install the clip, and the double-sided tape will hold it in place up off the bottom during installation. Same thing here on the pipe shoe. You'll notice that there's clips all the way around the top and the bottom, and there's space in between the shoe and the band of the top part of the clamp and the pipe to allow for air to circulate and evaporate the water. Also allows for visual inspection. At this point, you may decide that eye rod is a good solution for your particular project, and if you do, you should know that there are some cheap imitations out there that don't work so good. So let's talk about those. These are the ones that we see the most frequently in the field. UHMWPE, which is ultra high molecular weight polyethylene, or PTFE, which is Teflon brand. Our product is iRod brand pipe supports. Teflon is the brand name for PTFE. And you may have seen that, and a lot of people believe that this is the same or think that it might be the same. It's not. iRod is a proprietary material. There's nothing else like it on the planet. There's no other material that can do what this does in terms of supporting the pipe for a long time. Over here on the left, the UHMWPE and PTFE, you'll notice that the pipe has sank down or smashed the PTFE material, UHMWPE. This is creep. The material has failed to creep. And you'll notice in this image there's also a U-bolt in place. If the pipe has settled down or smashed down the material underneath it, then the pipe would have lowered, which creates a little space on the top. If that U-bolt is there to hold the pipe in place, but now there's space created, then the U-bolt is no longer doing its job and the pipe can move freely, which could cause damage to angles or flanges or connection points or valves down the line, which can be really, really costly. In the center here is Delrin. Delrin is usually black, but not always. You'll see here that not only is it smashed down, it's completely deformed out of shape. It's curved and completely formed out of shape because Delrin is softer than the other two materials over here. Just doesn't work very well. And then on the right here, the last one, this is injection molded plastic. It's a very brittle material. You can't get the same compressive strength by injecting plastic into the mold as you can by extruding the plastic from a machine, which is how our iRod and these other ones are made. This is a comparison with iRod, our standard wide iRod at the top and left here, and then HT and peak. This is comparing the strength on the left. You'll notice the strength going up on the left and the temperature range across the bottom. And you'll notice from the very beginning, our standard wide iRod is much stronger. It has the ability to carry a load longer. Compressive strength is higher than any of the other materials, including UHMWP and PTFE. And as the temperature increases, eventually our standard wide iRod will melt. It's a plastic. But when it gets about the range where it's getting a little softer and a little less compressive strength, that's when we start to recommend our HT. And if this chart kept going, the HT would fall off, and that's when we recommend peak. But you'll notice that in comparison of strength, our material is far superior to the other materials on the market. This is the injection molded, which was the last image on that slide before. You'll notice that on the ends of this, there's small circles just outside of the drill holes on both ends. And those small circles are where the plastic is injected into the mold. And that's how we know that this is injection molded plastic. Very brittle material, fails really quickly. While I was doing a presentation like this in Trinidad, they told me that our iRod had failed on a skid that had just arrived. This skid was manufactured in South Texas, delivered on a boat to Trinidad, had just been removed off the boat and set on the dock. So I said, let's go look at it. When we walked out there, I could see from a distance this piece that has failed here. But even from a distance, I could tell the shrink on the bolt was not the same. This is really thick, bumpy material. It was vulcanized rubber. We don't use rubber because rubber holds water against the pipe, and we don't like that. It's a bad idea. And this is cracked, which looks a lot like injection molded plastic, I thought, but we took it off, flipped it over. Sure enough, there was little dimples on the bottom side, injection molded plastic. So the operator asked me, how did we get that? We had written iRod into our specifications. We looked at it closer. Their specification said iRod or equivalent. And this is what equivalent got them. There just isn't an equal or an equivalent to iRod. This only lasted the boat ride, hasn't even put in service, and it's already failed. In comparison, this is what iRod looks like after it's been used in the field. This is the first offshore platform in the Gulf of Mexico that's specified IROD and had IROD installed in 1989. In 2002, we did an offshore inspection of that platform 13 years after installation, and the IROD and new bolt was still in place. You can see here on the far left image, IROD still doing the job, pipe still protected, no corrosion happening. 2017, we went back to that platform and did another inspection after 28 years of service. And you'll see the new bolt is still in place, pipe is still being taken care of, no corrosion damage. Some more images from the same platform. On the left is 13 years after installation, still doing the job. And on the right, this image looks really bad, I'll give you that. But there's no real difference in the damage away from the pipe support as at the pipe support. This really is more of a coating maintenance program issue with the operator. The thing I find interesting is the beam has started to bend, this beam has started to bend, but the IROD is still in place, still doing its job. So we say that cheap imitations are not a bargain if you have to replace them regularly. There's no equivalent to IROD, as I've mentioned. Imitations can fail immediately. Contractors can be liable if IROD is specified and knockoff is used. Just make sure that the supplier is providing IROD. The way to tell is that every single piece of IROD that we manufacture has our name on it, and it has a batch number. The batch number is there just in case there's some kind of issue in the field. We can go back and see if we did something with the mix on that batch, if something was wrong. We haven't had to do that yet, but we have some traceability here. Also, every order of IROD comes with a letter of authenticity. In conclusion, IROD is an inexpensive solution to a very expensive problem. It's good for new and retrofit projects. It has a 28-year plus design life, delivers the full life expectation of the coating so the coating can protect the pipe. Simple cold work installation, excellent wear protection, high compressive strength, and a wide range of applications as I've shown. IROD is specified by most major energy companies around the world. It's also specified by major industries including chemical, aerospace, public utilities, railroad, food processing, transportation, distilleries, and a whole bunch of others. There has never been a reported pipe failure when properly fitted with IROD.